All right, welcome to chapter 6. So in chapter 5, we expanded our idea of probabilities by looking at probability distributions. And now we are going to look at a specific type of probability distribution called a normal probability distribution, which will guide the bulk of our work in statistics. And so this is a very important step forward, and we're going to begin developing the tools now that we will use for the rest of the semester. So if we look at chapter 6, we have 5 sections. The 6th section is not covered. Normalized approximation to binomial is an extra section that we don't plan to cover at all. So you will not see that included on the homework or on any of the exams. But we're beginning with the standard normal distribution in 6.1, and that's what we're going to introduce today. So let's look at our key concept. In this section, we present the standard normal distribution, which is a specific normal distribution having the following 3 properties. 1, it's bell-shaped. The graph of the standard normal distribution is bell-shaped, and that basically means that it's higher in the middle and tapers off symmetrically as you go to each side. We've already looked at the idea of a normal distribution, but now we're applying the idea of a normal distribution to a probability distribution, and we're defining a specific standard normal distribution. And so properties of this standard normal distribution is like any normal distribution, it's bell-shaped. Number 2, the mean value is 0. The standard normal distribution has a mean equal to 0. So that means you have above 0 positive values and below 0 negative values. And the average or the mean value right in the middle being 0. And then the standard deviation, which describes how far the data is spread away from the mean value of 0. The standard deviation is equal to 1. The standard normal distribution has a standard deviation of equal to 1. So let's remind ourselves what this says about the data set. Remember that by the range, sort of the rule of thumb for standard deviations, if you deviate up to 1 standard deviation above or below the mean, you capture about 2/3 of the data. And if you deviate within 2 standard deviations above or below the mean, you capture about 95% of the data. And if I go 3 standard deviations above and below the mean, I capture well over 99% of the data. And so in this case, the standard deviation is 1 and the mean value is 0. So if you look at data values or scores in the -1 to +1 range, 2/3 of the values will be in there. And between -2 and +2, 95% of the data values will be in there. In this section, we developed the skill to find areas or probabilities or relative frequencies corresponding to various regions under the graph of a standard normal distribution. So we'll have to see what that looks like, and we'll be doing some problems graphically. In addition, we find z-scores that correspond to the areas under the graph. So we've talked about a z-score being a measurement of how many standard deviations you are above or below the mean when you're a particular data value. And now we're going to relate that to a portion of the area under the graph for the standard normal distribution. So that's a lot to do. Again, all of this doesn't usually make sense when you first read it, but sometimes you might want to reflect back on this first slide for the key concept and see if it's beginning to make sense as we illustrate and learn some of these skills. All right, so they begin by defining the normal distribution with a formula for sort of what the value is on the distribution curve with a y value based on some input value of x. You don't really need to know this for anything, so you can ignore it. but we can see they're reminding us of what this bell-shaped curve is that we've talked about in the past. And this is if you graph that formula for the standard normal distribution, you get this shape where in the middle, dead center is the mean, which we know is 0. And you have this symmetry of a high value in the middle, and then it tapers off as you move to the right or to the left symmetrically. All right, so what are some properties of this normal of distribution? Oh, I'm sorry. They're introducing now a different kind of probability distribution called a uniform distribution. And then they're going to give us the properties of a uniform distribution. So just to be clear, they just talked about the standard normal distribution, and now they're talking about something else. They're talking about a uniform distribution. A uniform distribution is not a normal distribution. So what are properties of a uniform distribution? The area under the graph of a continuous probability distribution is equal to 1. And that's going to be true for all of our probability distributions. You may recall from last chapter, the probabilities under different values have to add up to 1. The difference now is those were discrete variables where you had different output answers. Now we have a continuous probability distribution. So you have a nice smooth curve instead of just discrete values like the binomial distribution or something like that. But the area still, the total of all the probabilities have to add up to 1. And there's a correspondence between the area and probability. So probabilities can be found by identifying the corresponding areas in the graph using the formula for the area of a rectangle. The rectangle will be in the case of a uniform distribution. So we kind of need to see this graphically. So we can come back and read this again, but let's look at this. A uniform distribution is a continuous for a continuous random variable is when the values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. So let's see this. And so, well, let me skip ahead for a second to a uniform distribution graph. So here's an example they're talking about. It produces a rectangular shape. So this is what a graph of a uniform distribution would look like. And basically the idea is all the possible values you can get are all equally likely and evenly distributed. Then you get this uniform distribution. Now let's go back to this idea for a second and we'll look at that graph as it comes forward. So the uniform distribution is a continuous random variable where you can get different answers like anything from 0 up to 5 or whatever, and that they're all random, and continuous means you might get any variable in there. So instead of getting just discrete values like 0, 1, 2, 3, 4, 5, you can get a continuum of possible values. And so let's go ahead at this point. Now they're talking about a uniform distribution and make up an example that we can think about or refer to that's simple as we then look through these definitions a little bit more carefully. So let's say that I assign a random variable x to equal height of, we'll say a TV. Actually, I think I'll skip TV. Is not a good example because I want something more obviously continuous. Let's say we do a height of a, I'll just say a person. And so when you're looking at the height of a person, you could get any possible height value between the shortest possible person in your collection that you're looking at or the highest or tallest possible person that you're looking at. So if we have the height of a person, we can think of this as a continuous variable where any value of a measured height is possible within the range of smallest to biggest. So let's say you have a group of people and the smallest possible person is 4 feet and the highest possible person is 7 feet. So perhaps 4 is less than or equal to x is less than or equal to 7. And if you randomly pick a person in there, you just don't know what kind of a height you're going to get. And there may be millions of people in your population, and you may have practically a continuum of possibilities. Now, in this case, I think you would probably have a normal distribution, because I would expect if you looked at all the height values, sort of in a range, we'll say from 4 to 7 feet, that there would be more people in the middle and less people in the ends. So 5.5 feet is in the middle. I don't know, that's probably a little low for the average, but you would have maybe a mean value in here of maybe around 5 foot 7 inches. I don't know what the mean height is. And then you would have more people in the middle and then kind of a normal distribution around that. But this is an example where you could expect any possible height value in that range. So if instead we have a uniform distribution, then that would be something where whatever our range of value is, we'll say 0 to 10 for our variable, all the answers in that range are equally likely. And so when you have equally likely occurrences, then you don't have a lump in the middle where things are more likely. You have an even line because everything is equally likely and occurs equally frequently in the distribution range. Okay, so when you are making this graph that I'm talking about, and let's say you're talking about values from 0 to 10, for a uniform distribution, the graph that you get is called a density curve, because now we don't have individual values that we're saying how likely they are, because there's infinitely many values that are possible in this continuous range from 0 to 10. So what we do is we graph all those possible values, and in this case, if it's uniform, we'll get a line, and this creates what we call a density curve. Now, any density curve, whether it's a normal curve or a uniform curve, any density curve must satisfy the requirement that the total area under the curve is exactly 1. So if 10 is my highest value possible, I'll box that up there, and 0 is my lowest value. And then you can imagine that you could shade under this curve, and then the area should be 1. And if I have a normal, non-uniform curve and I shade under it, well, then that also should have an area of 1 if it's a density curve. Because the total area under any density curve is equal to 1, there's a correspondence between area and probability. And so the idea, just to give it quickly in a nutshell, and then we'll look at more examples, is in a uniform distribution, if I went up to the value, say, of 4, well, that would mean that since my curve is uniformly distributed from 0 to 10, that to the left of 4, I would have 40% of the area. Because if I go from 0 to 10, that's a 1. If I go from 0 to 4, 4 out of 10 is 40% out of the 1. 4 out of 10 as a fraction for how much of the area you have there is this equivalent to 40%. And so that you can get this connection where you could then say, when I'm looking at my uniform distribution, I'm 40% likely to get a value between 0 and 4. So if we have a normal distribution and things are working the same way, well, I don't know exactly where 40% would be. We'll have to figure things like that out. But for example, I know that right in the middle is the mean. And so since the mean is in the middle, then if you were to choose a value randomly, you would be 50% likely to get a value less than the mean, and 50% likely to get a value greater than the mean. And so when we're looking at a density curve, this is helping us make predictions about how likely it will be to get a value in a certain range, like greater than the mean or less than the mean or less than 4, things like that. All right, so they're going to use an example that's not quite so simple, or it has more context to it. And they're giving us 7 slides to look at this example. Waiting times for airport security. During certain time periods at JFK Airport in New York, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 and 5 minutes, as illustrated in the figure in the next page. So this is an example of a density curve, and it's modeling the uniform distribution for X being the values of waiting times in minutes, which have a minimum of 0 and a maximum of 5. And they say how long somebody will have to wait before getting help in the 0 to 5 range. All the possible times in that range are exactly equally likely. So it says, refer to the figure, see these properties, all of the different possible waiting times are equally likely. And you could basically see, because there's a 0.2 is the sort of expected waiting time for any period of time between 0 and 5. So how do we work with this? So again, what does this mean? The waiting times can be any value between 0 minutes and 5 minutes. Those are the possible outcomes, or the values of X, the waiting times. So it's possible to have a waiting time of 1.234567 minutes. The idea being this is a continuous variable, continuous random variable, instead of discrete, because even within that 5-minute time range, all possible answers might be achieved. And there's an infinitely different number of possible answers in that range, theoretically. Now, obviously, it may not be practical to measure down to the billionth of a minute or something like that, but theoretically, all possible answers are all possible answers in that range could occur, and there's infinitely many. So this is a continuous variable from 0 to 5. Now, by assigning a probability of 0.2 to the height of the vertical line in the figure, the enclosed area is exactly 1. Why is the area 1? Because we have a rectangle where the height of the rectangle is 0.2, and the length, or the baseline of the rectangle, is 5, because it goes from 0 to 5. And we know that the area is base times height, or length times width for a rectangle, and 5 times 0.2 is 1. And so why is this important? Well, that means because this becomes a probability density curve. Since the area under the curve is equal to 1, and the total of all probable outcomes is also 1, because we're certain that one of the outcomes will occur, then this can represent a probability curve that allows us to then use the area under the curve between a couple of values to tell us the likelihood of having to get a waiting time in that range. So given this uniform distribution illustrated in the figure, find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. So at least 2 minutes translates to 2 or more. And so if I look at where the 2-minute mark is on the graph, that's here. And 2 or more would be to the right of that. So the area under the probability curve here would be how long this portion is times how tall this portion is, because it's a rectangle. So going from 2 to 5 has a width of 3. And the height for any chunk of this rectangle is still 0.2. And so the area under the density curve for the values that are at least 2 minutes, meaning 2 or more minutes, would be 3 times 0.2, or 0.60. So the probability is equal to 0.60, or 60%. So what we're trying to illustrate here is the idea that when you have a likelihood of some value occurring with a continuous variable, like how long you're going to have to wait for airport security, going through airport security. If you have this probability curve, then you can calculate the probability that the result will be within a certain range of that continuous variable by looking at the area under the curve that covers that range of values. In a uniform distribution, that will always be some sort of a rectangle, and it's just base times height to find out what that probability would be. And we'll have to see how to do that for more complicated curves like a normal distribution. Questions, comments, discussions about this at all? All right, so there's a couple more slides for them to draw this conclusion, sum it up. Let's see what they have to say. The shaded area represents waiting times of at least 2 minutes. Because the total area under the density curve is equal to 1, there's a correspondence between the area and the probability of getting a value in a particular range. And we can easily find the desired probability by using areas. And so then they show us that shaded region. The probability of waiting time of at least 2 minutes would equal the height times the width of the shaded area for values of at least 2 minutes, which is 2 or more from 2 to 5. And so they shaded that, calculated the area, determined the probability was 0.6. And then they draw their conclusion to say that the probability of randomly selecting a passenger with a waiting time of at least 2 minutes is 0.6. All right, so having looked at the simplest type of probability graph for a uniform distribution, where all range of variable output values are rectangles, and you can just do base times height, we now look at the standard normal distribution. They gave us the little formula for that earlier on, but this is what the graph looks like. It has this nice bell-shaped curve. It has the 0 value in the center, and it has a standard deviation of 1. And so they're showing these standard deviation values along the bottom as z-scores. And so if we're thinking about this as a probability distribution, then for example, I can imagine right away, as I was diagramming earlier, that at the middle value, you have a 50% probability of being to the right and a 50% probability of being to the left. And earlier I discussed the range rule of thumb when you know the standard deviation. For example, we know that approximately 95% of the data will be between a standard deviation of -2 and 2, will be within 2 standard deviations from the mean. That means that you are 90%, you have a 95% likelihood of choosing a value in that range when you have a standard normal distribution. because that's the area is in there is 95%. So there's approximately 95% of the area between -2 and 2 for the z-score. Again, from last chapter, we want to remember the z-score tells you how many standard deviations you are away from the mean. Well, if the standard deviation is 1, then that matches up perfectly with the z-score. So now we're going to look at a specific example where we are given a z-score and we are looking up a probability. So I just sort of show we have some simple examples, like I know that a certain amount of the data will be between z-scores of -2 and 2, or if I have a z-score of 0, then there's 50% to the left of that, 50% to the right, because the 0 is where the mean is, right in the dead center. So now they say we can find areas or probabilities for different regions under a normal model using technology or table A2. And so I will illustrate how to do this in StatCrunch so we can use the technology approach after we go through some slides. But notice right away, they're telling us you're going to either look this up or use technology as opposed to using a formula or something like that. And they're saying specifically technology is strongly recommended. So I concur. Because calculators and software generally give more accurate results than a table, we strongly recommend using technology. All right, well, there's slide 1. So what are they going to do here? For slide 2, for finding probabilities when given a z-scores. If using the table, it's essential to understand these points. It's good to think about these points anyway, even if you're not using the table, just to warm up to the idea of a z-score, because using technology, you can make little mistakes, how you type into your TI calculator or something like that. And so having an idea of what you should get and being familiar with that is helpful. So let's take a look at what they say here, even though we don't really plan to use table A2. So it says when you are looking up probabilities based on z-scores, I'll point out number 2 here. It says the left page is for negative z-scores and the right page is for positive z-scores. So let's look at our graph here for a second again. Negative z-scores are over here, and positive z-scores are over here. And since the 0 right in the middle is at the 50% point, well, then if I have a score like maybe around 2, and I want to say, what's the probability of getting a value less than 2? Well, then that would be everything to the left of that 2, and that should be most of the data, much more than 50%. And in general, when you have positive z-scores, more than 50% of the data will be to the left of that. And when you have negative z-scores, less than 50% of the data will be to the left of that. Because positive and negative is separated right in the 50% mark at 0. And then it points out, as I was illustrating in that example, that each value in the table is a cumulative area from the left up to the vertical boundary above a specific z-score. So if you're using the table and the default is that you're always talking about to the left of a particular value, and meaning you would shade the area to the left of that value to get the score. Oh, that looks terrible. All right, so let's move on. Moving on. Now it does say when working with a graph, avoid the confusion between a z-score and areas. Z-score is the distance along the horizontal scale of the standard normal distribution, corresponding to the number of standard deviations above or below the mean. If you're still a little shaky on chapter 5, that sentence is probably completely confusing. But that was the idea of what a z-score is from chapter 5. And so, for example, in the graph we were just looking at, it's normal to have a z-score perhaps of 2. But notice 2 can never be a probability, because all probability values are less than 1, or between 0 and 1 inclusive. And so if you're talking about the area under a curve, that will always be a number that never exceeds 1, whereas z-score could easily exceed 1 or be negative. A probability value will never be negative. The part of the z-score denoting hundredths is found across the top row of the table. If you're trying to use the table, again, we're going to use technology. So formats used for finding normal distribution areas. Cumulative area from the left is most common. The following provide the cumulative area from the left to a vertical line above a specific value of z. You could use the table A2 in the book. You can use StatDisk, you can use Minitab, you can use Excel, and our choice, hopefully for most of you, is StatCrunch, and I'll demonstrate that at the end of the session today. The area between two boundaries is a little harder and can't be used in as many things. It's harder, you can't really do it in StatDisk. The table doesn't do it. You have to do some extra stuff. But notice the two ways you can find the area between two boundaries. StatCrunch is one of them, making it easier for us to find the area between two boundaries using StatCrunch and technology, and not without having to do extra work that you would have to do if you were using Excel or the table or something else. So again, I'll be demonstrating StatCrunch to make that easy to see. Now let's look at this example for bone density, and we are about halfway through the slides now. We'll try to look through this example a little bit, and we've got about 20 minutes left. So after this example, I'll leave the slides and go look at a StatCrunch problem from our homework. So in this example for bone density test, it says, a bone mineral density test can be helpful in identifying the presence or likelihood of osteoporosis. The result of a bone density test is commonly measured as a z-score. The population of z-scores is normally distributed with a mean of 0 and a standard deviation of 1. That's the standard normal distribution. So these test results meets the requirement for a standard normal distribution. The graph of a bone density test scores is as shown in the figure. A randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density test score less than 1.27. So they're telling us the answer that they got from the table, but you want to imagine what the goal of the problem was. Find the probability that a person has a bone density test score of less than 1.27. And again, the bone density test score is a standard normal distribution. That means a score of 1.27 is going to be a z-score. So they're showing graphically, you would mark off where the z-score is at 1.27. That's above 0, positive, so that would be to the right of 0 somewhere. And then you would imagine that the probability of getting that score or less than that score would be the area under the density curve to the left of that score. So they've shaded that in green. And when they looked up that z-score on their A2 table, they got an area of 0.898, meaning the probability of getting a bone density score of less than 1.27 is 0.898, or a little less than 90%. And we, instead of you getting that value from the table, can look that up on StatCrunch. Questions, comments, discussions about this? Okay. If you're feeling lost, let's take a minute or two here to see if you can become more engaged with the discussion. So if there are no questions, then I have a question for you to see if you are wrapping your mind around this correctly, or to just stimulate some questions or some conversation. So here's my question. What would be the expected value for a person who takes the bone density test?
I would guess that my guess is that it would be 0, because I mean that's in the middle of the distribution, right?
That's exactly right. And the peak of the curve is above 0, meaning that that's the most probable outcome, the most likely outcome that has the highest probability. So I wanted to stop and try to get us to think about what is going on here, because a lot of times for students, they really don't know what this curve is. And the program and the slides at this point just are assuming you understand what this is from their description, and usually people don't. And this becomes a very opportune place for students to completely start to lose grasp of what we're talking about. And that will, as we are at the stepping stone of the rest of the semester, this is a key time to really try to understand what the graphs mean, what they're referring to. And so the idea here is you have a real test, this bone density test, in which people take a test and there's a score determined on the test. And the kind of scores you get are like 1, -1, 2, -2. You get a score. And the test has been designed so that the scores are are normally distributed with a standard normal distribution. What that means is that the most likely result is a score close to 0. And the further your score is away from 0, the less likely that result is. And this graph is illustrating that. And the area under the graph will show you how likely it is, what the probability it is of getting a score in a certain range, like less than 1.27 in this case. So we want to try to wrap our minds around that as soon as possible in order to follow along with what every example is showing us, what it's trying to teach us, and to improve our understanding. If you're just looking for what you do, then your understanding will not be strong enough to progress through the rest of the semester. All right, so let's see what they say here. Note that the following are the same because of the aforementioned correspondence between probability and area. The probability that the bone density test score is less than 1.27 would be the same as the shaded area where you shaded the value under the graph to the left of 1.27. The amount of shaded area and the probability of getting a score below 1.27 are the same. So for the solution, we need to find the area. Well, how would you find the area under that curve? Well, for us, that's going to be looking up our table or using technology. So here they give an example of how they looked it up on the table. As you can see, it can be done, but it's not a friendly process. It's much easier using StatCrunch. So take a look at this if you plan to use the table, and you're welcome to do so, but I would instead recommend you use StatCrunch, so I'm going to move on. And they're saying, hey, we looked it up on the table and we got that answer. And therefore we conclude the probability that a randomly selected person has a bone density test below that score is a little less than 90%. Another way to interpret this is that in general, about 89.8% of people have bone density levels below 1.27. That's why the curve is the way it is, because as you move up and get values with higher scores, it becomes more and more likely that somebody has less than that score when you have a very high score. Imagine you're talking about how tall people are. Well, when you start going up over 6 feet, most of the people are shorter than that. And the higher you are in that range of values, the more likely that if you randomly pick somebody, you're going to get them to be less than a particular height. Let's see if this is where we should stop. Now they talk about finding area to the right of a value. So what that would mean if you're using the table, which only tells you values to the left, is that you would find that value to the left, and then you would use the complement rule, subtract that from 1 to get the area to the right. But in StatCrunch, we can do that graphically very easily instead. All right, so I think I'm going to stop here because we don't need to go through 4 slides to show us something that's easy to do on StatCrunch. All right, so if I come over to our homework assignment, so this is the homework assignment due this week. And again, this covers sections 1 through 3. So problems from section 1 should be in the first third or so. I'm going to go to question 5. Yeah, this looks basically what we were just leaving the slides with. Find the area of the shaded region. The graph depicts the standard normal distribution of bone density scores with mean 0 and standard deviation 1. So in the middle here would be a 0. So a z-score down at a -1, it makes sense where they've placed it. It's to the left of the 0. But they want us to find the region to the right of this z-score of -1.07. Now, what you could do is look this up on the table. If you look up this z-score on the table, you'll get the area to the left, which would be the blank part. And then if I subtract that from 1, I'll get to the right. But instead, let me demonstrate how to do this in StatCrunch. So finding the area under a certain portion of a standard normal distribution density graph is a type of calculation. Now, we don't have any data to use, no data set, so I'm going to simply open StatCrunch. And notice this problem has a video showing how to do it. It has a worked example, but let's just open up the tool in StatCrunch. So I'm going to go to Stat, Calculators, and what we want is a normal calculator. So Stat, Calculators, Normal, and we get this little normal graph. And it has some windows where we fill in the ones we know, and the one we don't know will be left blank, and we'll hit compute, and it'll give us that answer. Now, this will be for any normal distribution. The standard normal distribution is where the mean is 0 and the standard deviation is 1, and those values have been filled in for us already. In 5.2, we'll start to work with non-standard normal distributions where those may change, and we'll use this same calculator, and we would just enter ones we have when they're not 0 and 1. But for a standard normal distribution, the mean will be 0, the standard deviation will be 1, and those are the default for this calculator. Now, what we want is the area to the right of -1.07. That corresponds to the probability of getting an x value bigger than -1.07. And so I can set that probability here, and then it will tell me what that's equal to. And so the answer we will want will be in this bottom right field here. So I would say that I want this to be greater than or equal instead of less than or equal. And I would change the score from 0 to be -1.07. And I would hit compute. So the picture should match this. That's our hope. They showed the scale here. We can see that's just a little left of -1 because it's -1.07. But other than that, they look like they're matching the basic idea. And then this gives us the probability to more decimals than are required in the problem. Are there questions about how I just found the area to the right of a particular z-score for a standard normal distribution for this problem number 5 on our homework? Questions about how I used this tool or how I found it in StatCrunch? I want this to 4 decimals. So I'm gonna have to round up that 6 at the end to make it a 7. And that's the whole problem. So if you know how to use this tool, this is like a 10-second problem. So let's say that I just maybe got about 4 minutes left, see what the next problem looks like. So for this problem, they're giving us access to the table if we wanted to use, but we don't. And also in this problem, they're asking us to find the z-score, and they gave us the area. So on the previous problem, they gave us the z-score and wanted the area. And in this problem, they're giving us the area and they want the z-score. The graph depicts the standard normal distribution. Find the indicated z-score, and what's shown in the graph is that the area left of there is this. So when we just used the tool for problem 5, we typed in the z-score and which way we wanted to shade, and they gave us the probability. So in this case, we're going to change to less than or equal, because that's the part shaded here. But instead, we don't know the z-score, so we'll leave that blank. And instead, they tell us that the probability to the left of the score is 0.9808. So for problem 6, we would enter the area that we want to be as indicated and leave the z-score blank, and then when we compute, it fills the z-score in for us. And we want that rounded to 2 decimal spots. And then we check our answer. So you can see we can use this tool given the area to find the z-score, or given the z-score to find the area. We can use the tool either way.